What is the number of disjoint cycles of length greater than 1 in the permutation this? We have to find number of disjoint cycles of length 1. So this permutation is given, and 1 is going to 5, 5 is going to 3, 3 is going to 7, and 7 is going to 1. It means that cycle is 1, 5, 3, 7. This is closed cycle. Because of 1, 3, 5, 7 is used. So remember, remaining one is element 2. 2 is on 2. So this is cycle of length 1. Now 3 is used. Come to the point 4 or symbol 4. 4 is going to 6. 4 is going to 6. 6 is going to 4. Means this is cycle of length 2. And asked about cycle of length greater than 1. So remove this point. So the cycle of length 1 we normally not write. It means that 1, 5, 3, 7 this is one cycle, and 4, 6 is another cycle. So there are two disjoint cycles. So option A is correct. In group theory, which one of the following statement is correct? Abelian groups may have non-abelian groups. If abelian group, then group and subgroup have the same binary operation. Also, elements are coming from abelian group, so they will form commutative property. That's why non-abelian group doesn't exist. So, subgroup of abelian group must be abelian. So, statement first is correct, but by the word non-abelian, this statement becomes wrong. So first statement is wrong here. Now come to the second statement. Cyclic group may have non-cyclic subgroup. Cyclic group have subgroup. It means that identity element will be same, and identity element generate whole subgroup. So it will be cyclic. So again this statement is wrong. Now come to the option C. Non-abelian groups may have abelian groups. This statement is correct because of we know that matrix multiplication is group but non-abelian group. But in matrix multiplication we are considering all, suppose Hermitian matrix. So it may be abelian or not, but you can consider this is matrix multiplication, and in general or precisely you can consider GLNR, or restrict this GLN means up to order 2, means matrices of square matrices of order 2, and subgroup consider because of this have non-zero determinant, and consider subgroup as diagonal elements only have, means only diagonal matrices. Then diagonal matrices, product of two diagonal matrices will be same. It means it will become commutative property or become abelian subgroup of this. So non-abelian groups may have abelian group. This statement is true. Non-cyclic groups cannot have cyclic subgroup. Again this statement is wrong. Non-cyclic subgroups cannot have cyclic subgroup. It can have. So only statement C is correct. Let G be a set. In this set AB and AB are real numbers and A is not equal to 0, means order pair in which first element is non-zero. Be a group with respect to a binary operation star on G. Define as if we are taking two elements means two order pair, then order pair combined by this method. For all two order pair, then the inverse of element 2 3 which is belonging to group G. We are finding inverse of an element particular 2 3. Inverse of 2 3 we have to find out. So question mark. We can only find inverse whenever we know or have the idea about the identity element. Now, what is identity element? Identity element of this group G, and we know that identity element is unique. So first we are going to find identity element. By the definition of identity element, if we take an element from the group, if we operate identity with an element, then it returns same element. Using this definition, we are going to take an element of G means an order pair AB, and suppose identity element is C comma D, that will return element itself. How these two elements combine? By the definition of binary operation, you can see AC comma BC plus D is equal to EB. And these two order pair are equal. It means AC equal to A and BC plus D is equal B. Now solve these two. Take common. A C minus 1 is equal to 0, and I already taken A is non-zero as defining element in G. You can see here A is non-zero. If we are taking an element in order pair, then first element is non-zero and there is no condition on second element, means second component of the order pair. We know that A is not equal to 0, so C equal to 1. Call it equation 1. Now from this one, take B. C minus 1 plus D is equal 0. Means transpose these two. Means taken in same side, and after that B is a common. So C minus 1 plus D. This is only calculation. And we have the value of C. Means B 1 minus 1 plus D is 0. This is going to be 0. So D equal to 0. Means we know the element CD. Now value of element CD is 1 comma 0. This is identity element E. Call it identity element. Now find inverse. Inverse of inverse of the element 2 3. The inverse of this element, suppose CD is the inverse of this. By the definition of inverse, this operate with these two will return identity. And how they combine? 2C comma 3C plus D equal to identity element is 1 comma 0. So 1 comma 0. These two order pair are equal. This implies that 2C equal to 1 means C equal to half, and 3C plus D equal to 0. Value of C is half, so 3 by 2 plus D is equal to 0. This implies D equal to minus 3 by 2. Means CD is nothing but half comma minus 3 by 2. Now check which one option is giving half minus 3 by 2. Option C is the same. So option C is correct answer. Let A be an element of a group G such that A raised to the power 10 is identity and A raised to the power 25 is also identity, and A is non-identity element. Then the order of element A is. As given, a raised to the power 10 is identity. It means that order of A is less than equal to 10. Also, order of A divide 10. Second thing is a raised to the power 25 is also identity. This implies that order of A is less than equal to 10 and order of A will divide 25. Sorry, this is also 25. So combine these two, it means that order of A is less than equal to 10 and order of A divide common factor of 25 and 10. Means order of A will be the common factor of 25 and 10. It means that order of A is 5. How? You can write 25 as 5 into 5 and 10 also 2 into 5. This means that this only is a factor which can divide both 10 and 25. So order of A is 5, so option C is correct. Let G be a non-abelian group of order 125. Then the total number of element in center of G is how many elements? Number of elements in ZG, or you can say cardinality of ZG. Order of G is 125 and G is non-abelian. Non-abelian. Keep remember one point. If order of G is p raised to the power q, where p is prime and G is non-abelian, G is non-abelian, then order of center of G equal to p. Means here 125 is given, can be written as 5 raised to the power 3. So order of ZG will be 5. So option A is true. This result is true for all primes.